Now, Introduction to Sustainable Aviation. Today's lecture. Very briefly about me. I'm a doctoral student at ETH Zurich and at Paul Scherrer Institute. Paul Scherrer Institute in the group for technology assessment, and at ETH Zurich at the Department of Mechanical and Process Engineering, and Professor Russell McKenna's group for energy systems analysis. My background is in physics and engineering physics, and the topic of my PhD research is life cycle assessment of future air transport systems. I completed my private pilot's training about 2 years ago and have been enthusiastically flying ever since. Now, the research that we do, both at Paul Scherrer Institute and ETH Zurich, is of course concerned not only or not primarily with aviation, but aviation as one of the most hard-to-abate sectors, or sectors with hard-to-abate carbon emissions, is of particular interest to us, and we have aviation domain experts in our group, including our group head, who has a background in aerospace engineering from a university in the United Kingdom, and then various researchers who deal with questions of sustainable aviation fuels and the supply chain underlying them. We've in the past collaborated with various entities of the Swiss government, with the European Aviation and Space Agency, Airbus, Synhelion, and EMPA. So if students are looking for either a bachelor's, master's, or project thesis, I encourage you to check the websites. There's various opportunities. Of course, we're not as hands-on as some of the student projects that actually build aircraft, either hydrogen or battery-powered, but we take a system-level approach. So if you're interested in modeling, computer science, I encourage you to take a look. Now, something definitional. Sustainability, of course, is a very broad term, an umbrella term, but what I'll be focusing on in this lecture, also because that's primarily what I've been dealing with in my own doctoral research, is sustainability in the environmental sense. So we won't be delving too deeply into the economic implications of, for instance, switching to different fuels. But we'll take a look at sustainability in the sense that we'd like to continue flying for the foreseeable future without accumulating environmental burdens. Now, why did we add this lecture to the lecture series Aviation II? I think it's rather obvious. Over the past years, sustainability has come to the forefront of both industry and academia in aviation, not just in aviation, but in aviation in particular. And I'm sure many of you have already heard that, for instance, at the European Union level, and this includes Switzerland and the European Economic Area, aviation has now been added to the ETS, the European Emissions Trading Scheme. There's international legislation that is affecting aviation. We'll get into this a little later in the lecture. So the United Nations, ICAO, has implemented efficiency standards. And as you can see, both academic research interest and search interest of the general public has risen sharply over the past years. And I've just added a selection of industry reports on sustainable flying, sustainable fuels, and so on. So the small ones and the big ones, the big three management consulting agencies now have dedicated teams trying to assist airlines in their sustainability transition. So we thought it would be a good idea to some degree fact-check current efforts and contextualize many of the reports that no doubt you've received through either publications like this or through mainstream media. We are in Switzerland, of course, very fortunate to have for considering the size of the country, very strong aviation industry, and I've just selected a couple of entities, and of course there is no mention of completeness here. Entities in Switzerland that deal with sustainability in aviation specifically. So, for instance, the European Flight Academy, that's training aspiring Lufthansa and Swiss Air pilots, is soon to transition to battery-powered DA-40 aircraft, therefore decarbonizing completely at least one part of the flight training of aspiring pilots. We have Swiss, who is active in the adoption of sustainable aviation fuel, as is the Lufthansa Group at large. IATA has entire teams working on assisting airlines in both meeting the reporting standards for emissions that have been implemented by ICAO and in transitioning to more sustainable fuels. Skyguide has projects, so The club has hosted an event only very recently where we had Christian Weiss, senior staff from Skyguide, mentioning what they're doing and trying to decarbonize Swiss airspace. So the goal of today's lecture is perhaps not so much to prepare you for the exam. As many of the students who've already taken Aviation 1 know, there's only 1 or 2 questions from this lecture that are going to make it into the exam, but it's much more trying to get you a high-level overview of the topic and contextualize, as I've mentioned, other reports. So how much carbon is global air transport emitting? What are the non-carbon impacts of aviation, which are significant, unlike in other sectors? What net zero scenarios have been proposed? How efficient can future aircraft get? Is it prudent to use a linear trend in trying to extrapolate future aircraft efficiency? What are the main challenges in decarbonizing aviation? Can we electrify aircraft? Of course, a DA40 aircraft is a 4-seater. Depending on how heavy your passengers are, this isn't going to be viable for many routes within Europe. So can we produce non-fossil fuels? How many of them? And then finally, the most interesting part of any aviation lecture, it's air law and regulations. What emissions regulations apply to aviation? So the table of contents is as follows. We have a short introduction that's supposed to motivate the lecture, aviation and the environment, aviation and technological change. No simple solutions, which is a bit unfortunate, but at the same time, perhaps the reason why I have to hold this lecture in the first place. Then a brief section trying to split up the topic into 3 levers that are accessible to us or accessible to policymakers, and that is increasing efficiency, making fuels non-fossil, or at least decreasing the carbon footprint of the fuels, and regulating aviation. So that could either be carbon taxation, carbon offsets, efficiency limits, fuel blend mandates, flight bans, as has recently been introduced in France. A little spoiler alert, even though evidently a flight ban has been imposed on some short-haul domestic routes, none of them are actually affected, so that's quite the case study in how a bill becomes law, and then an outlook at the very end. Good. Short introduction. So maybe just for context, the first flight, the first powered flight, 1903, Wright brothers in Kitty Hawk, a 12-horsepower motor, flight distance just short of the wingspan of the Lockheed Super Constellation, which was incidentally also the last aircraft that Orville Wright was ever able to fly in a flight that was organized by, well, the name eludes me now, but shortly before his death, he was able to take to the skies again in a commercial passenger airliner where the wingspan was larger than the flight distance he had covered in his initial flight. 1970s essentially, although of course design study started in 1944. The Concorde, cruising speed of in excess of 2,000 kilometers an hour. Thermal efficiency of the engines 43%, so in excess of, to my understanding, any other man-made thermodynamic engine at the time. Retired in 2003, 20 builds, and this is essentially where we are today. The Airbus A380 entered the market around the year 2000, design studies from 1972, 250 built. Although unfortunately, not a commercial success for Airbus. So why care about aviation? Well, in over 100 years of aviation, air travel has become ubiquitous and infused every aspect of modern life, not just commercial air travel, it's also airmail, it's connecting far-flung distant places where there was essentially no intermodal competition, like the Seychelles or other outlying islands. We have had various rescue operations that were enabled by large-scale aircraft, and this is where we are today. This is a live picture of the sky above, well, it's centered around Switzerland, but it's really Europe. And I think you can even check where the aircraft are flying. So zooming into Switzerland, and maybe checking, coming back from Thailand. Well, so you can see air traffic has grown well, almost exponentially. I'll have some data on this, but I think it's instructive just to zoom out a little and get a visual feel of the amount of air traffic that's currently airborne. Now, passenger flights are part of the air transport system. What we're looking at in my research group is specifically intermodal competition, so rail, automotive, and air transport. And to give an idea of the prevalence of air transport, depending on the distance traveled, what you can do is try and plot this with distance traveled on the x-axis and the modal share on the y-axis. And this is for 3 different countries. And I'll be taking guesses as to which of these graphs shows which country. So I have the European Union, it's quite the broad average. I've got the United States of America, and I've got Japan. We've got the orange color being rail transport, blue being aviation, and red being automotive. The image at the left is any guesses as to which country this could be? Yes, that's the United States. It's quite astonishing that people in the United States still mostly take the car at distances over 1,000 kilometers. But that's the way it is. You can see that despite the, well, significantly more developed rail infrastructure in Europe, passenger rail infrastructure anyway, the modal share of aircraft over distances over 1,000 kilometers is significantly larger than in the United States. Somewhat surprisingly, this is also the case for Japan, although in Japan a primary issue is the cost of high-speed, long-distance rail connections. The same goes for freight. Even though air freight is around an order of magnitude more expensive than the next best mode of transport, that either being rail or freighter, we can see that by value, this is almost universal, except in some countries which are have their economy tilted toward the resource extraction. The share of the economy, or the share of goods transported by air, is around 40%. And this already gives you an idea of how difficult it is going to be to decarbonize aviation, or at least even through policy measures, enact effective measures to reduce unnecessary, if you will, air travel. Because even for cases where there is significant economic advantage, there is still a large market for air transports. And we had Martin Tyler in the Aviation I course, who is an expert in air cargo, worked for CargoLogic for a long time, and the students that took Aviation I may remember some of the advantages of air transport when it comes to other modes of transport. Now, the growth of air transport is tightly interconnected with economic growth. We can see that as world GDP has grown, this is in tera US dollars on the x-axis, so have the absolute numbers for passenger flights. You can also see the freight numbers. One interesting thing here for the 2 COVID years, 2020 and 2021, unfortunately I don't have data for from 2021 onward. You can see there's a market difference, obviously, in passenger flights and freight. So passenger flights obviously decreased, and some of these flights were used to transport medical equipment into Switzerland, which is why the trend in the decrease of air freight has not been as marked. Now, this is interesting. Of course, this is about as aggregate as you can get, looking at global GDP and global numbers of passenger kilometers. What's more interesting is to learn where will growth come from in the future, is to look at different countries. Now, I've color-coded this such that at least the bubble of the color should give you an idea, not of the country specifically, but of the continent. I've just marked 3 countries. We've got GDP per capita, so this is essentially income or household income. It's a proxy metric for household income on the x-axis. And then we've got per capita, or absolute number of passenger kilometers flown on the y-axis. And this is a figure that's prominent in all the growth forecasts of the large OEMs. Boeing, Airbus, they all show these kinds of figures to their investors. And up until recently on a log-log axis, this was a straight line. But the significantly stronger than expected growth in Asia means that now the large bubbles, India and China, are significantly above the line. And I'll show in just a minute what this actually means for emissions. But what is reasonably well established is the regression or the correlation between personal income and the propensity for air travel. What's also reasonably well established in economic literature is the bidirectional relationship between economic growth and air travel, especially in developing nations, which essentially translates to if you can't fly between two cities, there's going to be very little commerce between the two cities. So we can expect, as developing nations hopefully transition to service economies, out from purely resource extraction economies, emissions from Africa and Asia to grow significantly, especially Southeast Asia. Now, emissions. Air transport is currently responsible for roughly 2 to 3% of global carbon emissions. That number has remained somewhat constant. I've tried to find here the split of global carbon emissions by sector. It's quite difficult to get these numbers, actually. You would think that in the age of the United Nations Sustainable Development Program and all these statistics that are put out every year, there would be a good split of sectoral emissions going back to, I don't know, say the 1950s, but there is not. So it took quite a while to compile these numbers. Using actual fuel data to calculate aviation emissions. You can see that the majority of emissions is electricity production, so that's called power industry in this graph, and transport. Transport is the gray area, and the yellow area being explicitly or specifically air transport. In the years 2020 and 2021, or between the 2 years, so for one, you can see the COVID slump. You can see that in all sectors. And for another, I've tried to contextualize this because this is in megatons of CO2, and I don't really have a handle on megatons personally. So aviation has been responsible for about the emissions that Bitcoin mining and all of cloud computing have been responsible together. Now, of course, you have to consider that cloud computing and Bitcoin mining could be very easily decarbonized. So perhaps the comparison is a bit mute. But this is what we're dealing with in terms of carbon emissions. Unfortunately, and I'll get to that in a couple of slides, the non-CO2 emissions, so that's any other warming that comes from, for instance, changes in cloud cover, persistent contrails, direct interaction of radiation with aerosols and so on, is also significant and at least on the same order of magnitude as the warming that can be attributed to increase in carbon emissions. Now, of course, you could say we should, or you could ask, how quickly could we reduce the amount of carbon emissions by, for instance, banning domestic flights or short-haul flights or flights up to an arbitrary number of kilometers or number of hours flown? Unfortunately, I have data or I was able to find data for the United States and for Europe, and the majority of emissions comes from long-haul flights. So the data sources here really are completely different. So on the one hand, it's from Eurocontrol, on the other, it's a study with support of the United States Department of Energy. And you can see that in the spinning that I've added to the figure here, so up until 500 and 500 to 1,000, 1,000 to 1,500 and so on, the majority really does come from very long-haul flights. Of course, the efficiency or the fuel burn per kilometer or per passenger per kilometer does depend on the trip length also. I have a diagram of that on the very right side here. Obviously, for very short distances, the emissions aren't great because a lot of fuel is burned during takeoff. And as the share of takeoff when compared to cruise decreases, so does fuel burn per kilometer until fuel uplift, which is essentially the rocket equation, you have to carry fuel to be able to burn it in the first place, kicks in. But so simple solutions, again, won't really work because the majority of flights cannot be decarbonized. So the only bin where people are actually considering battery electric aircraft for I don't know, up until 50 passengers would be the very left one. So that's up until 500 kilometers. Okay, so how about growth? What you can see here is total number of aircraft in service worldwide, starting in the 1950s. It's also quite hard to get that data. I've here attributed the Soviet Union to Asia, I believe. And what you can see is that while Europe, in terms of aircraft in service, and this is by country of registration, has been somewhat stagnant, at the very least until from the 2000s, the majority of growth has come from Asia. So only this year or at last year's Paris Air Show, Indigo, the country's foremost low-cost airline, ordered 500 A320 aircraft, or at least confirmed previous options, and then ended up with 500 confirmed purchase options for Airbus aircraft. Now, of course, you might say China has expended significant resources in developing their domestic high-speed rail network. This has been all over the news, in the United States especially, when, for instance, the efforts in California to build a rail connection between, Los Angeles and San Francisco has essentially stalled since 10 years. The Chinese have essentially built an unprecedented number of rail kilometers. You might ask, can we actually see this here? The interesting answer is no. The reason is this, and I encourage you, if you're interested, and I think this, as it is essentially a good case study of the challenges that we might face in trying to decarbonize the transport sector, I encourage you to look into the research into this, is what researchers have found is up to 1,000 kilometers, with a peak at 700 kilometers, high-speed rail connections in China are highly competitive over air transport. So what people have found is significant decreases in passenger numbers. However, the country or the country's population has gotten so much wealthier that this replacement has been completely offset by people flying either internationally to other locations within Asia or Southeast Asia, or domestically, because China is, after all, a very large nation, over connections where high-speed rail is unviable. So it's a bit of a sobering result. In the year 2001, many papers were published asking, well, how will Chinese aviation companies survive? Well, the answer is the country got a lot richer, so now there's a market for both high-speed rail connection and for aviation. Of course, aircraft in service is sort of an interesting metric, but there might be less efficient aircraft in South America than there are in Europe. So what I've also done is I've had a look at the actual fuel emissions or fuel expenditures, which directly translates to carbon emissions in these different geographies. Here I was able to find good data only from the 1980s. For data prior to 1980, I had to use declassified CIA intelligence reports that try to estimate the fuel production capacity of the Soviet Union and China. And here the growth in Asia is really stark. So Europe, through a combination of, well, more efficient aircraft and a smaller rate of economic growth, or certainly growth of income, so GDP per capita, has stagnated since the 2000s, and the majority of growth has come from Asia. You can see the COVID slump. I tried to find more recent data, but unfortunately this is only released every couple of years. So yeah, in terms of emissions, it seems there is indeed an issue. About these emissions. So we've seen that it's difficult to decarbonize aviation because we can't just ban short-haul flights, and even if we did, that wouldn't really make a dent in the overall emissions. We've seen where growth has taken us. Now the question is, what are the actual emissions that we care about in aviation? Here I've classified emissions other than CO2 as other emissions, which is essentially noise emissions, particulate matter, and NOx and other soot particles. Now, all of these are essentially beyond the scope of this lecture. We will have an aviation expert from the Federal Office of Civil Aviation, Theo Rendlisbacher, who's active in various committees of ICAO, actually writing the legislation that tries to find a trade-off between, for instance, fuel efficiency, so thermal efficiency in the turbofan engine, and NOx emissions. And I would ask you to direct all questions on these emissions to him. There's some visually striking images, so we have made strides in, for instance, reducing particulate matter, because there's no more water-resisted takeoffs, at least not in civil airliners, and even in the military ones. There's now more or less high bypass turbofan engines. In terms of noise emissions, relatively stringent rules are in place. In fact, to my understanding, there is a chance that if noise emissions, which have been successively, or the emission levels have been successively lowered by ICAO, continue to be lowered in this way, we might actually be able to grow globally noise neutral, which is a bit of an interesting term, but this would just mean that the global blanketed area that receives more than 50 decibels of day-night average sound would almost stay the same over the next 20 or the next 30 years, even at currently significant growth levels. So you can see that this is, I think, for I don't quite know what decibel level this is, might be 79, but what you can see on the lower right here is how the blanketed area has decreased as per the different noise emission standards. And above that is an image that shows essentially the same for Zurich airports. So what we are more interested in this lecture is warming effects of aviation, and this could be contrail cirrus. So these are high-altitude cirrus clouds that form from contrails. Could be low-altitude clouds that form from soot particles that are emitted into the atmosphere. Could be contrails themselves, although that's a negligible part. Could be sulfur in the atmosphere and other soot, and of course carbon dioxide. Now, before I show a figure that shows you how much the atmosphere is actually warming from aviation, from both CO2 and these non-CO2 warming effects, I'll briefly have to show this for context. What this shows is that there's two different kinds of emissions that we care about in aviation. One is the long-term emissions, which is carbon dioxide. This accumulates, you can see on the right-hand side, if aviation continues at present levels or even growth, then the levels of carbon dioxide, and from that resulting, the radiative forcing on the planet will increase, whereas there's short-term effects, like essentially all of these cloud effects are short-term on the timescales that we're interested in climate science, and they're essentially an emissions pulse. So in the left figure, we are assuming an emissions pulse at time 0, and you can see that radiative forcing, and this would of course be a rather long-lived cloud if it actually stays up in the atmosphere for 20 years, but for visual consistency, I made that a very long-lived cloud. It decreases over time. Now, there's different metrics that you may or may not have already heard. There's global warming potential, there's global temperature potential, there's radiative forcing, there's effective radiative forcing. You don't have to care about most of them. What I'll be using will be effective radiative forcing, Strahlungsantrieb in German. The unit is watts per square meter, and this gives you a time slice in the warming equation, essentially. So, effective radiative forcing from aviation. At the very top, we have CO2 emissions. All of this data is from a very large meta-study that looked at all different climate studies that have been published on aviation over the past 40 years, scaled them to current levels, because for the cumulative effect, you actually have to give a date for which you provide effective radiative forcing, because it accumulates, so this is 2018 levels, and then ran statistical analysis to average the results. There's relatively low uncertainty on CO2, so we have a pretty good understanding of the surface temperature increase from CO2. You can see that the error bars grow very much larger for the other effects. So directly below CO2 we have NOx emissions, nitrous oxides. Unfortunately, most of the non-CO2 warming effects are complex, either physically or chemically. So physically, those could be cloud formation, that's poorly understood. There's an entire research group of the German Aerospace Center, DLR, in Oberpfaffenhofen that does only non-CO2 warming effects. And I've spoken to two of the researchers in preparation for the lecture. And this is centimeters per second updrafts that go into these models and essentially change the outcome from cooling to warming in these simulations. So it's complex physics or complex chemistry, like in the case of nitrous oxide emissions. We have methane that's formed or broken up. We have ozone that's formed or broken up. In fact, it's both formed and broken up on a short and a slightly longer time frame. And it ultimately adds up to the lowest bar, which is slightly warming. And already almost on the same order of magnitude as CO2 emissions. We have soot radiation trapping, which is essentially as the atmosphere becomes more hazy, radiation is reflected back to the Earth. We have sulfur radiation trapping, sulfur being a very good climate forcer. 2 years ago, the International Maritime Organization, IMO, finally mandated that heavy oil and fuel oil that was used in maritime shipping had to be sulfur-free, or at least sulfur-free to the degree that the haze that essentially blanketed global shipping routes disappeared. And to my understanding, we can already measure the effect. And this is a slightly warming effect, I believe, because as you can see here, sulfur is actually cooling as it reflects light back into, or it reflects infrared radiation back. And then we have all the different cloud formation effects. The only one I've included here at the very bottom is contrail and contrail cirrus cloud formation, which is very much significant. So you can see that, well, I mean, the upper part of the error bar is certainly twice as large as the best estimate for CO2. And even the lower error bar is on the same order of magnitude as CO2 emissions. There is a caveat. This is effective radiative forcing, which means that rapid radiative adjustments have been taken into account. So this means contrails form, and from these contrails, long-lived cirrus clouds form. But along with that, other clouds, or the water vapor that would have otherwise gone into other clouds, disappears. That's a short-term or a rapid adjustment. This has already been taken into account into this metric. However, there are slow feedbacks also. This includes changes in the Earth's albedo, other cloud formation, different distribution of water, etc., etc., etc. And once you figure this into effective radiative forcing, you get what's called the efficacy. So this means this would be one step further from here. And the efficacy that latest studies have found, at least for contrails and contrail cirrus, is only 30%. So for this one specific effect, it's actually significantly smaller than we had thought. And we would need to do the same kinds of simulations for all these effects. This is all very complicated, and I'm really quite happy that what we'll be focusing on for the rest of the lecture is mostly CO2 emissions. It is interesting, but it's quite the challenge reading the publications, because all of these climate papers are at least 20 pages long with a 50-page appendix. But you're lucky because I've summarized it for you. So we have a good understanding of CO2. We know that non-CO2 effects are generally complex. Cloud formation, something which I had not, natural cloud formation that is, something which I had not included in the other figure, is generally believed to be cooling overall, but with very large uncertainty. So some data from NASA and other universities in the United States suggest up to 200 milliwatt per square meter, which would put this here, which would mean that aviation would essentially be geoengineering cooling the planet, which would certainly be interesting. But as so often, more research is needed. Efficacy for some of the effects is small, which in turn means that you may have heard about this. This was in the news about half a year ago. Google and Delta or American Airlines collaborated with Google providing or updating short-term climate models, or actually weather models, to help airlines avoid regions in which contrails can form, which essentially be like this. You fly from JFK to Frankfurt, you know that in some of these regions, you know that on the date of the flight, you know that in some of these regions contrails are more likely to form. You know that generally, from this figure, contrails have a short-term warming effect. You'd like to avoid this. So what people have suggested is making part of the airspace more expensive to fly through. This is very ambitious, not least of all because short-term weather forecasts are very difficult to generate. Google claimed very good results. I think they had a 2% fuel burn increase from rerouting or flying at different altitudes and a 50% decrease in contrails. But at the same time, a low efficacy in actual contrail warming would call this into question. So I would be very skeptical if any of these kinds of measures will be introduced in the short run. Also, because of this, contrail formation depends not just on the partial pressure of water in the atmosphere and the current temperature in the atmosphere, which gives you a rough estimate of which gives you a condition under which contrails will be formed. It also depends on the exhaust temperature. It depends on the size of the soot particles. What you can see here is a relatively old 707 on the right side with low bypass ratio General Electric's turbofan engines, and a more modern A340. And they fly at the same altitude, and the 707 does not leave contrails. Now, when I spoke to the people at DLR, they said, yeah, this figure is very interesting because the thermal efficiency of the A340 is much higher than the 707, so it burns at higher temperature. And I thought, that's interesting, because I actually thought that was the size of soot particles. And it is a combination of both. I briefly checked what the exhaust temperatures are for the 707 and the A340. Of course, I don't think I was able to get numbers at cruise thrust, but at least at what is breakaway thrust, like 20% of max takeoff thrust. You can get numbers, and they're really low. And the difference between the 707 on the top and the A350 on the bottom, or is it the A350? Oh, so I took an A350 there for whatever reason, is very low. And the reason for that is also because the bypass ratio, of course, of the A350 is much higher. And I'll get to that when I talk about aircraft efficiency. But essentially, the engine does a better job of cooling the exhaust. So in a couple of slides, we'll look at whether actually has climate effectiveness or the climate impact of aviation changed over time. The answer is yes, it has, but it's very difficult to quantify. So there's flights that are currently ongoing, trying to find out whether sustainable aviation fuels will have impact, etc., etc. Okay, so how much has aviation actually improved since the 1950s? And how much can we expect it to improve in the future? Well, it has improved by a lot, actually. Certainly more than any other mode of transport that I was able to find data on. I mean, there's really only 3. I like this figure because it's for the United States, and I'm going to have you take a guess what happened in 1973. Yes, exactly. Well, one of the many oil crises, or well, the OG oil crisis. It's really funny, actually. So the 2 major shocks, the 2000s energy crisis and the 1973 oil crisis, were responsible for significant improvements. So the Department of Energy introduced policy and funded research, etc. And the same is essentially true for aviation. So the next question is, why was there a significant increase in the energy intensity between 1950 and the 1970s for aviation? Yes, exactly. This is fleet-level data. So in the 1950s, well, in 1950, there was no jet aircraft, no commercial jet aircraft, and then they were introduced. So it really makes sense to compare the 1970s to today, but because I was able to find data all the way up to 1950, I decided to do that. It's essentially this. Steam power, diesel power, electric power. This is also captured here. So I do have rail data going back all the way to, I think, 1850 in the United States. And what you can actually see is there's still some steam engines that are being replaced in the figure before. The issue is, of course, if you have higher efficiency in any appliance or service that consumes energy, what do you expect? Do you expect people to consume the same amount of the service or the appliance? No. This is called the rebound effect. And while I won't go into this in detail, we should keep this in mind. If there is no rebound effect, what this means is Efficiency in these figures is the incline, the slope of the lines. You consume the same amount of energy from the service, but due to higher efficiency, you consume less. You consume more of the service, you consume less electricity or less energy. If there is rebound effect, generally you expect to consume more of the service and thereby offset some of the losses. Of course, well, one part of the rebound effect is marketing, and this has been especially prevalent in automobiles and in cars, but now, no simple solutions, or the reason why we have the lecture on sustainable aviation. Why not just electrify aviation? Well, the issue is essentially this. What I have plotted here is on the x-axis, the gravimetric energy density, so how much energy is there per kilogram in an energy carrier, and on the y-axis, the volumetric energy density, so how much per volume. Kerosene, which this might actually be an issue because kerosene in English isn't quite the same as jet A1, but it's about the same. It's between kerosene and gasoline. Is all the way up there on the far upper right. Hydrogen, of course, there's a split in the axis, simply because the gravimetric energy density of actual liquid hydrogen is very good, so about 3 times that of jet A1, German kerosene. Aviation fuel. And then on the lower left we have batteries, and that's a bit of a disappointment. We'll have to zoom into that, which we can do here. So there's the same axis, just zoomed in. Gravimetric energy density, which is more relevant to aircraft, and volumetric on the y-axis again. Now, the different colors correspond to different battery chemistries. The most prevalent, of course, being lithium-ion batteries, which are used from anything as small as this to the Tesla cars, which many of you may be driving. And I've shown, and I think this is really instructive, the historical progress in the capacity of these batteries. Because, I mean, when they were invented or when they were first commercialized, they certainly didn't have the same capacity as they do today. So you can see that for lithium-ion batteries, we start all the way down here in the 1990s. And 2020, so the blue rectangle is the average, the industry average, if you buy an off-the-shelf lithium-ion battery for presumably automotive use. And then the best performers are the little dots. We have 2 forecasts here, and I've added the physical limit. So this is, it's a very information-dense graphic, but this gives you all the information that you will need to assess whether you can actually replace aircraft on certain routes with battery electric aircraft. And for that I have data on the bottom figure. The bottom shows for commuter and for turboprop aircraft what share of the routes you could replace. This is based on estimates by the International Council of Clean Transportation. So the way we would read this is as follows. Well, that's helpful. We currently have an energy density of, like 150 watt-hours per kilogram. That allows us to replace maybe 20% of commuter aircraft in the United States if we make them 15% less heavy. That's for lithium-ion batteries. At the physical limit, which at least according to current scientific estimates will almost reach, we'll be able to replace over 70 or over 50% of commuter aircraft in the United States if they're 15% lighter. Of course, no one's actually considering using lithium-ion batteries. What people are thinking is more exotic battery chemistries that are not yet in use, including lithium, or not in use commercially, lithium air, lithium metal, and so on. I've added the physical limits for those also. So 2 of the limits are here. And current prototypes is this blackish gradient here. So NASA, Northrop, Wright, and Cattle, which I think is a Chinese or a Taiwanese manufacturer, are all working on batteries for electric aircraft, and they're all the prototypes, not the projected future capacity, is all in this range. So this means that there is hope to electrify aircraft on commuter routes, certainly. Turboprop aircraft, some of them, all of course depending on progress in batteries. Progress in batteries is of course very much dependent on the number of batteries manufactured. This is called Wright's law. It's essentially a different version of Moore's law for processors, with Moore being improvement over time and Wright being improvement over implementation, so number of batteries manufactured. Okay, so we can't electrify aircraft, or at least not all of them. So why don't we synth fuel our problems away? Why don't we use biofuels or synthetic fuels? Well, I mean, we can. Actually, you can if you fly to New York using any of the Lufthansa Group airlines, then you can purchase sustainable aviation fuel that will be blended into the mix. Not just for your specific flight, because for certification reasons, not all aircraft can fly on 100% SAF. In fact, very few can fly on 100% SAF currently. But much like with fair trade chocolate, Mengenausgleich, mass balance, this is added to other flights. Unfortunately, it's a little more expensive. So current prices, I don't know how many of you have already purchased a ton of jet fuel. Goes about $1,000, puts you back about around $1,000 currently. And SAF is all the way up there, in excess of 2,000. Singapore Airport wants to mandate all departing flights use SAF from, I think, 2026. But even the most liberal estimates from consulting agencies like McKinsey believe that this is going to be very much limited by the availability of synth fuels or biofuels in Singapore. Anyway, that's the forecast. Industry forecasts have this interesting tendency that whenever it's about implementation, they all grow exponentially, and when it's about reducing emissions, they fall exponentially. So you can see that here. Before I give you a short break, just some of the forecasts that are currently being used to try and estimate how we can get to net zero emissions by 2050. 2050, of course, being a very nice round number, no real bearing on reality. This is from Destination 2050, which Destination 2050 may be the European industry consortium, Waypoint 2050 being the American consortium. What you can see here is green is SAF, sustainable aviation fuels, includes biofuels and synth fuels. Red is market measures, which is newspeak for making flying more expensive. Operations and infrastructure would be, for instance, single European sky, so better routing, free route airspace. Technology is obviously efficiency improvements, and you can already see that there are significant differences between them. So the Europeans, of course, love regulation, or they are more realistic about regulation entering the market. The Americans very much are counting on rebate programs by the United States Department of Energy on SAF. Eurocontrol is a little more on the operations side, naturally. And the people in St. Gallen believe we can just offset emissions forever. That's of course a bit of a misstatement, sorry for that. But here it's much more about offsets, and I'll get to offsets in the second part of the lecture, but it's more about that. I've tried to compare them, and the lecture slides obviously are going to be made available. But yeah, you can see that depending on the geographic locale, the policy environment, and the incentives behind whoever makes these forecasts are quite different. And after the break, a 10-minute break, we'll go into all these different levers. So we have efficiency, we have policy, we have decarbonizing fuels. And that's essentially it. The key points are only for those that take the exam. So those are relevant. And I've added further reading and domain experts for your benefit, because the great thing about the course in general is that the guest lecturers are actually the people writing the legislation or informing the people who write the legislation. Have a good break. Okay, please take your... Ist gut. Also theoretisch noch zweimal diese Einheiten. Okay. We might be experiencing some turbulence. Please take your seats. Well, I hope you're all rested, because now comes the technical parts, the fun parts. I'm going to show you an equation and I don't expect you to fully follow this, also because it's not really relevant. The relevant part comes on the next slide, but I would like you to have seen it at least once. This is called the Kaya identity. It's essentially a derivation of what's called the IPAT formula, and all these funny names just go to say this is one way to split up the different levers we have to decarbonize anything, any sector. Energy consumption, GDP, CO2 emissions, and populations all go in there. Essentially means if you have a given population, if you have the GDP per capita, if you have the energy intensity per capita and the carbon intensity per energy, then you end up with carbon emissions. Now, what's more interesting to us in aviation is if we adapt this slightly. It also makes this a lot easier. We have carbon emissions on the left side, E over T being the energy intensity per passenger kilometer, F over E being the carbon intensity per energy, and then the traffic. Now, this formula gives us 3 factors, and along these 3 factors, we will briefly proceed with this section. We have aircraft efficiency. This would be new designs, new fuselage designs, new engine designs, new materials, etc. We have the fuel carbon intensity, which in this case is fixed. Generally, in the Kaya identity, this is of course dependent on the electricity mix, but in case of combustion engines, this is all in the carbon intensity of the fuel itself. And then we have the traffic, which is a proxy for the cost of flying or the availability of flying. Now, you may have heard of Paul Ehrlich, a researcher, most prominent, I think, in the 1970s and 80s, had warned against the population explosion and the carrying capacity of the Earth. And in his original IPAT equation, there was also the idea to reduce the world population, but since I have not yet degraded to the moral level of Paul Ehrlich, we'll be taking that aside for the moment. Now, if we split up aviation emissions, efficiency, and traffic according to the Kaya identity, which I've just shown, we can see this. And I think this is actually really interesting and very instructive. It's a log axis from the so it's a log axis on the y-axis. The linear axis is obviously time. We can see that, well, the first thing, the carbon intensity itself has remained constant, because right now we're burning fossil fuels. This, of course, is an approximation only, because the energy return, or energy use on energy return of different kinds of oil blends is different, and also there is some blend of non-fossil fuels in the mix currently, 0.05% in Europe and 0.01% globally. But even more interestingly, and you remember this from the part on non-carbon emissions, or warming effects, non-carbon warming effects, this has changed significantly. But in any case, we'll take this constant for the time being. Energy intensity has decreased by 49%, and again, it's a bit of an issue having this at the fleet level from the 1950s, but it would only have decreased more if we start in the 1970s or 1980s. Traffic has gone up by, 30,000%, and emissions by 1,000%. Let's start with aviation emissions, aircraft efficiency. How has efficiency changed, and what are the physical limits, and how much can we expect this one lever to still contribute to decarbonizing aviation as a whole? The 1950s benchmark is the de Havilland Comet, the first commercial jet airliner, a venerable aircraft that developed from the 1940s, first flight 1949, continued in service in a slightly modified version in the Royal Air Force until 2011, which I think is rather impressive, 110 built. Today's benchmark is the Boeing 787 Dreamliner, first civil airliner with a composite fuselage, 80% composite by volume. Engines now, instead of having a 0:1 bypass ratio, as was the case in the Comet, now has a 10:1 bypass ratio and over 1,100 built. If we look at aircraft efficiency, what scientific reports and forecasts usually do is they say, at the fleet level, over the past 10 and 10 and 10 years, so the past 30 years in 10-year steps for whatever reason, we've seen a decrease of 2.4% annually compounded, which is quite impressive and the result of new aircraft entering service currently. But it's a very difficult metric to use because it's a compound metric and it really hides the fact that improvements in very different areas of material science, physics, and chemistry have led to this trend. So what you actually have to do is not look at the overall efficiency, but split it up into engine efficiency, aerodynamic efficiency, structural efficiency, which essentially is a metric that describes how heavy the aircraft is in its ability to carry passengers and freight, and operational efficiency, which could be things such as load factor, so how full is the aircraft, but other things such as off-block time, how far the actual route or the track deviates from the Great Circle route, etc., etc. And all this makes up ETA, the overall aircraft efficiency or energy usage. Overall efficiency in units of megajoule per available seat kilometer, I'm calling that ETA here. There's various ways you can calculate this from open source data. Generally, this is a metric that is highly proprietary and closely guarded by OEMs. If you have ever had to deal with climate models or traffic models at the European level, you may know that Eurocontrol has good data called BADA, the base aircraft database something. But even there, they do have the actual metrics provided by the suppliers. You have to sign a waiver saying that you won't compare two values. It's quite the disclaimer there. So we used open source data to estimate this from the first commercial jet airliner. So here we're excluding all piston-driven aircraft. And we can see that, well, first of all, we can see that the Comet 1 and Comet 4 seem to be very different aircraft. Does anyone have any guess why that is? How we got from, 9 megajoule per available seat kilometer to 3.5? There's a hint. There's a cutaway drawing of the Comet 1. It's really all essentially in the number of passengers you can fit into the airplane. The Comet 1 was a business jet for all intents and purposes. This was the actual seating that they had intended for the Comet 1. The Comet 4 was the real predecessor of commercial aircraft as we know them today. So if you fit twice the number of passengers in there, then obviously you reduce energy usage by half. I've included fleet average. Why are there some points that are worse than the fleet average? So why would you build an aircraft that has a lower energy or higher energy usage than the fleet average?
Because it's a fancy aircraft with a fancy interior and less people inside.
We've excluded. So you're clearly describing the Gulfstream series of business jets, my favorite. But no, we've excluded those. What this is smaller aircraft. But what you can see here is aircraft that are optimized for long range and for short range. So an Embraer 175 would have, we found, worse efficiency than, for instance, a 787, simply because it is optimized for takeoff and landing rather than cruise. So if we actually exclude the Comet 1, which, as I've mentioned, is really a business jet, and we're excluding other business jets as well, we get something like this. And we get to the, 2.4% decrease in energy usage per year over the last 30 years. And the question is, what was responsible for this? And fortunately, I had a master's student who was very good, by the way. We have spots for new master's students, if you're interested. And what I did with that master's student was disaggregate efficiency improvements in commercial aircraft. So we actually had a look what was responsible. Was it the engines? Was it the aerodynamics? Was it the structure? And what we found was this. Between 1958 and 2000, the majority came from engine efficiency improvements, the rest aerodynamics and structural. You can already see that it's a game of diminishing returns currently, and that over the past 20 years, aerodynamics have played the largest parts. Okay, we can start with structural efficiency. Let's delve into the sub-efficiencies. Structural efficiency just describes how heavy the aircraft is in relation to its utility in carrying passengers and freight. It's actually very difficult to find a metric that does all the aspects of an aircraft justice, including its speed, its range, its capacity to carry passengers and or freight. So what we've done is, we had to do this from publicly available data, we've used the operating empty weight over the passenger exit limit. Now, at the very end of the lecture, I'll get to something that ICAO has done to try and measure this, which is slightly different. We've used passenger exit limit, which is a certified limit rather than a technically feasible limit. And that limit, of course, is also dependent on aircraft doors. So how many passengers you're allowed to fit into a plane is dependent on how many you can evacuate in 90 seconds, if I got that correct. And this is dependent on the number of doors and the size of the doors, etc., etc. So it's really an approximation, but it's the best we have. And the interesting thing is, I've mentioned that the 787 is 80% composites by volume and like 60% by weight, I think. But we don't really see a good trend here. And of course, you have to split this up between wide body, narrow body, and it seems 2 times narrow body. I'm guessing this is narrow body for regional routes or something. And you don't really see a trend. And we looked into this specifically for 2 aircraft, the 787, which is mostly composites, and the A330. I think the Neo, but that still is mostly aluminum. And we found that the A330 has, in the variants that we compared, shorter range and is also slightly slower. So this means the metric isn't able to capture everything. Some things it does. We also see that lower is better. Wide bodies generally slightly worse. Aerodynamic efficiency. We're essentially just using lift over drag. So if you remember Jörg Wildi, who has the aerodynamics lecture in Aviation 1, lift over drag we calculated by solving for it in the Breguet range equation, which I think Louis Breguet introduced, which we're able to, into which we're able to plug in the data that we have, and what we find then is this. And this is much more interesting, or visually appealing, if you will. There's been significant improvements for a number of reasons, but what we find is that for a tube and wing design, so the fuselage design that's currently most prevalent, there is what we have approximated to be a physical limit at around 25. And this is considering, for instance, the size of the aircraft on the ground, the size of the aircraft in the air. So the 777X, for instance, will include foldable wingtips for it to remain on the ground within certain box limits that are relevant to aircraft stand size. So that's an economic limitation. But we're essentially approaching the physical limits with current fuselage designs. There's some improvement still. I think Swiss recently introduced their shark skin, nano-textured foil made from polyethylene recycled bottles that gave them a 1.5% efficiency increase, I think, without fuel uplift. But this is diminishing returns. What you can see here also is that narrow bodies really are not optimized for cruise flight when it comes to lift over drag. Of course, one way to go above the current limits is by using blended wing bodies or a strut-braced wing. So strut-braced wing is the illustration on the left, and the blended wing body is on the right. I think Blade is a current Airbus or Boeing project. And this would be one way to still improve efficiency when it comes to aerodynamics. Engine efficiency is interesting because, as we've seen, between 1958 and 2000 was responsible for the majority of improvement. We've split this up again into propulsive and thermodynamic efficiency, or thermal efficiency. You can approximate both propulsive efficiency by using exhaust velocity and velocity of the airplane, and thermal efficiency by using ambient and compressor exit temperature. The thermal efficiency is essentially the efficiency of the Brayton cycle. So turbofan engines fall into the category of the Brayton cycle. And once you do this, you find that fuel burn has improved, is essentially dependent on the bypass ratio, which is hidden in the propulsive efficiency equation. Generally, higher bypass ratio means lower overall exit velocity. And we're rapidly approaching viable limits. This is only half interesting. What's really instructive is if we actually split up engine efficiency into propulsive and thermal, and then plot that. So we can see that, and here the color axis is essentially the year of introduction. We can see that the most recent engine generation, including geared turbofan engines like the Pratt & Whitney 1100, are in this cluster of lightly colored dots, and first and second generation turbofan engines are somewhere here. The physical limit for thermal efficiency is non-negotiable. This is a matter of thermodynamics. The physical limit with respect to NOx emissions is very much a matter of negotiations, and it actually is so in the most operational sense of the term, in that there's actual negotiations at the international level, at ICAO, and Theo Rindisbacher from Basel, who will hold one of the other lectures, so I encourage you to speak to him about this, is actually one of the people who has supplied test data, I think in collaboration with Helvetic Technik, or Swiss Technik, for the agency to make these determinations. Higher core temperatures mean higher thermal efficiency. I think most of you have solved not a Brayton cycle, but maybe a Carnot cycle in your thermodynamics or physics classes. But higher temperatures also mean higher NOx emissions, and these are limited already, especially in the vicinity of airports, but also internationally. I've added some efficiencies here, so the engine that drove the 707 was around 20% overly efficient, and today we've almost doubled. Now, operational efficiency is the last of the efficiency metrics. The only thing we've looked at here, because it's such a complex metric that again hides how far do routes deviate from the Great Circle route, what is the actual airborne time, what is the turnaround time, etc., 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 is seat load factor, which is how many seats on average are filled. I'm going to have take you a guess. At the fleet level, what is the current seat load factor of the international airline fleet in percent? It can't be higher than 100. That would be illegal.
60?
Good guess, although maybe you're flying routes where there's not so much demand. It's actually a little higher. It's actually very high. Before COVID, it was approaching 80, 90% at the global level. For some routes, of course, this is even higher. At least on all the Ryanair flights I've been on, it's certainly been higher. It was maybe even approaching 100. I've added rail transport occupancy rate also, just as a comparison. It's a bit of an apples to oranges comparison because rail transport serves a different purpose than air transport, at least in Europe. But still, Deutsche Bahn has an impressively high average occupancy of 50%. So that's the one thing. This, by the way, was also this contributed significantly to overall energy usage reduction. So just making sure.
I just want to, in defense of Ryanair, from all the trips in DB I took, I think that they are on 120 of occupancy.
Yeah, certainly feels like that. Was it Ryanair that suggested that people actually stand in the back of the plane? Well, that would be approaching 100 or going above 100. Yeah, no. I mentioned that we wouldn't go into this, but just because I was able to make such a nice figure, I'll show this also. Operational efficiency also includes route deviations. And since part of this lecture is supposed to further your ability to ask critical questions, I don't know if you've actually read the My Studies description. I've 4 routes here, and there's, I think, 8 reasons for which the actual track deviates from the Great Circle track. Can you name all of them?
The most prevalent one over the Himalaya is because the safety system of the oxygen mask doesn't last long enough to reach a low enough altitude.
Yes, that's one. That's safety and geography. Yes? Yes, that's geopolitics. So they can't fly over Russia, and they're voluntarily choosing to avoid Ukraine, which I think is also in the interest of all passengers. The same with Afghanistan. So this is actually a rather unfortunate position for Finnair to be in. But I think their track actually increases by 1,400 kilometers. So geopolitics, airspace closures, safety and geography. I think there's a couple more missing. At least the two that you can see nicely, or three. Yes?
Flyover fee?
Say again?
Flyover fees.
Yes, although Finnair still chose to fly over Russia, and as far as I understand, their overflight fees are rather expensive.
I think the Air France flight might have deviation in airports, so if the ETOPS rating is not there.
Exactly, ETOPS. So this is a limitation that essentially mandates that aircraft with only 2 engines always remain within a certain distance for which they are rated of a deviation airport. And the interesting thing here is, this is a bit of a special flight. This was a delivery flight of an Airbus A220, a Bombardier C series, from Montreal to Charles de Gaulle. And evidently, the ETOPS rating, maybe only on that specific flight, or maybe for the aircraft in general, wasn't high enough, so they actually had to fly closer to Iceland. So that's another thing. I think you can see 2 more. Yes? Yes, excellent. That's the one from Manila to LAX. So over the Central Pacific, there's no airspace closures, I don't think. So they actually chose to stay within prevailing winds, or well, maybe not jet stream in this case. And there's one more. This would be on London Heathrow to Johannesburg. This one's my favorite.
I think you can see the strike of the French.
Yes, the French are always on strike. So we could save the climate by just forcing them back to work. Yeah, so there's a couple of reasons. There is research into how much the collapse of communism actually improved aircraft efficiency by Western airlines being able to overfly Russian airspace. Of course, we're in the reverse now. But this is all, unfortunately, beyond the scope of this lecture. Okay, well, the key points were looking at fleet level efficiency is only somewhat instructive. You need to look at sub-efficiencies, engine, aerodynamics, and structure, and operations, if you're interested. Energy intensity has decreased compared 90% to the Comet 1, but it's a bit of an unfair comparison, and 75% compared to the Comet 4. Fleet level, around 50. The rate of improvements are likely to diminish unless revolutionary rather than evolutionary approaches are adopted, at least in fuselage design. You've seen that with the strut-braced wing and blended wing body. And potential for improvement in operational efficiency is small, but efforts are underway. Here I would actually encourage you to read some of this after the lecture's over. This is very interesting research, trying to really understand at the high level how we can improve the entire fleet, efficiency of the entire aircraft fleet. Okay, so in the Kaya identity, we've looked at efficiency. We can now look at fuels, more specifically non-fossil fuels, because that would sort of be the whole point. Generally, when we talk about non-fossil fuels, we're talking about 2 kinds of fuels. We're talking about biofuels, or fuels derived from biological sources, or feedstocks, and synth fuels, or fuels derived from synthetically, i.e. industrial chemically produced feedstocks, such as captured CO2, syngas, etc., etc. So on the left, we have a rapeseed field somewhere in Germany, used for biodiesel production currently. And on the right, we've got a solar power plant, not for thermochemical reactions, such as the Synhelion startup that ETH is trying to do, but for electricity production. But in any case, that's the idea. Now, how do you even measure the carbon footprint of fuels where the supply chain is really complex? Because the supply chain of these non-fossil fuels is really complex. Even the supply chain of fossil fuels is rather complex if you actually include the entire life cycle. The oil rig needs to be built. There needs to be maintenance on the oil rig. You need to actually ship the oil from the desert somewhere to a refinery, etc., etc. The refinery has losses. All that incurs carbon emissions. The method that's used to do this, and this is the expertise of the people in our group, and dare I say my own expertise, is life cycle assessment. It's a standardized methodology. There's an ISO standard for it, although that is rather vague. And that essentially determines the emissions that are incurred throughout the entire supply chain of a product or service. And the associated environmental burden. So this is a rather simple supply chain for the case of fossil fuels. But if you, instead of Jet A1, you want Biojet A1, then this might be what the significant part of your supply chain might look like. So you might not, in fact, start with the drilling, but you might start with the drilling further upstream because you need nitrogen fertilizer, and most of that comes from either natural gas or through other chemical processes that require oil. And the biomass then goes into a silo, it's fermented, you get biocrude, you refine this. The issue here, of course, is that, I think this is a pretty good approximation of the supply chain for biojet fuel, but in reality, this would look something like this. You get lots and lots and lots of more inputs, and actually determining the carbon footprint, which is the only relevant metric in the policy context, can be very complicated. There's two groups, research groups in the United States that deal with this. There's one at MIT, the MIT LAE, Lab for Aerospace and the Environment, and there's one at Georgia Tech. It has a large aeronautics program, and the group at Georgia Tech actually calculates the carbon footprints that go into these tables that the ICAO, the International Civil Aviation Organization, has prepared that determine which supply path or which fuel path has which carbon footprint. I'm not a chemist or not a chemical engineer, but I will give you a very short overview of the different pathways that you can have to get to these different non-fossil fuels. So first we have biofuels, and they have this nice logo here spelling out CORSIA. I didn't write down what CORSIA actually means, but it's the ICAO program that does two things. It tries to increase the adoption of biofuels. It determines which fuels are biofuels, or eligible biofuels in any case. And it has an offset part to it. So it's not like you have mandatory carbon tax, but it's a mandatory carbon offset on some flights. We'll get to that in the legal part of the lecture. You can have different kinds of biomass. One is lignocellulosic. One is oil-based, and one is starch and sugar. Starch and sugar we're sort of disregarding because, rightly so, the European Union, and I think also ICAO, has determined that food shouldn't be fuel, even though at the present moment the European Union is producing more biodiesel than would be required to fuel all domestic flights, and that biodiesel naturally grows on agricultural soil. But what people actually think about when they say biofuels, they usually mean lignocellulosic, and that's via fermentation or gasification pathways or extracted oil pathways. There's two processes that are going to be relevant for the exam, and not just for that, but for anyone with an interest in the history of, well, civilization, really. And that is, one, the Fischer-Tropsch process, which was developed in 1926 and was significant to the German war effort in World War II, unfortunately, which converts syngas, so carbon monoxide and hydrogen, into liquid hydrocarbons. Germany had small amounts of naturally occurring natural oil deposits, so they liquefied coal by this method. What are the carbon footprints, or what are the environmental burdens of these different fuels? Well, according to our colleagues at Georgia Tech, those vary widely. We have three things. We have carbon emissions per megajoule, availability in megatons, and price. The first thing, you can see that even under the most optimistic scenario, which I've always chosen in this case, the price will remain almost prohibitively high all the way up until 2050. There is, of course, a significant deviation in the price of fossil kerosene, and I've included that in the range here, but it doesn't even come close. So that's one thing. The other is that at least for lignocellulosic biomass, there should be enough. Less so for oil-containing biomass. This also has a non-negligible moral component. I think Nestle is a large producer of palm oil in and around the Johor Islands surrounding Singapore, and they have a vested interest in making that an adopted fuel. One more interesting thing, I get carbon emissions that are negative. How do I get that? If only we had LCA experts here. Yes?
Okay, so maybe because during the whole process, more of the biomass, so like the part of plants, they actually take more CO2 inside than they later on give in the...
Yes, I mean, that's the only way it can physically work. It's essentially right. It comes from something that's called indirect land use change, or ILUC. These specific crops that make up the majority of the, as you can see, that's a distribution, so the majority of these fuels actually enrich the soil, so they sequestrate carbon into the soil, at least when compared to the crops that would have otherwise grown there, according to these studies. So there's that. It's a matter of which study to take and the assumptions. It's a bit unfortunate I can't go into this a little more. But this is the way it looks. So we would have enough, it would be very expensive, and the carbon footprint wouldn't be that bad. Now, synfuels are slightly different. There's no biological precursors. Instead, we have nitrogen, electricity, water, and CO2, captured either from, or captured during industrial production, or directly from the air. There's a Swiss startup that tries to do this in Iceland. And there we have the other process, which you should be interested in if you want to pass the exam, or if you're interested in the history of civilization, which is the Haber-Bosch process, which does what? I'm sure everyone's heard of the Haber-Bosch process. Yes, it turns nitrogen and hydrogen into ammonia, which is the precursor for industrial fertilizer. So it was the dynamite of the population explosion. And unfortunately, the reason World War I lasted 4 years and not 1. Because again, Germany didn't have natural deposits of nitrogen, unlike the British did. So there's that. The pathway that is interesting to ETH students, or should be interesting, is this one. The solar redox cycle is something that an ETH startup is actively developing. Aldo Steinfeld's former group, professor just now retired, Department of Mechanical Engineering, has been working on this intensely. There is a metal catalyst that is first oxidized at 1,500 degrees and then reduced at 1,500 degrees and then oxidized at 900. And that again turns syngas, so a combination of carbon monoxide and hydrogen into fuel. You can, of course, also generate hydrogen from electrolysis directly and put that into airships, which isn't something people do nowadays, following certain security-related incidents. But these are all the synfuel pathways that are relevant. For completeness, I've also included fossil fuel synfuel pathways, because there is a significant interest both in terms of research and in terms of scaling up from the militaries around the world, including some interest from Arma Swiss, and of course the United States Army is one of the largest research agencies into non-fossil fuels. This is essentially the pathways that I mentioned earlier, relevant to German war efforts in the 2 world wars, and starts from coal.
Going to have clean coal, really clean coal.
And maybe if we have clean coal, it will be a non-fossil fuel, who knows? Natural gas and nitrogen. Now, these are the pathways, so it's not so complicated. One thing I have left out is the refining, so there's other processes in there, but that's the gist of it. Now that we have the fuel, can we actually fly with it? And That's a good question. Yes, we can. Unfortunately, that's more of a certification issue than a technical issue. There has been a flight, is that November 28th? So I'm guessing that was then. So 3 months ago, across the Atlantic using 100% SAF. SAF made from, did anyone actually read the press release? Did anyone hear about the 100% SAF flight? Do you know which pathway that was? It was oil. It was recycled cooking oil. So maybe Belgium will save the planet.
Gonna have
Currently, all Airbus aircraft are certified to fly on 50% blend of fossil A1 and either bio or synth A1. Efforts are underway to speed up the certification process. And I think the very right one also mentions what I alluded to earlier. Singapore wants all departing flights to use SAF. But then the question is the scale-up. The question is the scale-up. Do we have historical precedents for scale-up of these processes? The answer is yes, historically. The issue for synfuels is, of course, the electricity mix. And I think on the very next page, I'm including a publication from our group that showed that if we actually want to make all the synfuel that we need to fly at current levels from electricity, which is the synfuel pathway, that would need, 5 times the current electricity production in the European Union? So we better hope that the ITER experiment in France finally produces more energy than it uses. But we have precedents. Now, key points. 0.05% of all flights in EASA countries, or 0.05% of the fuel in flights in EASA countries are using synfuel, or part of the blend is synfuel. There is enough capacity, although this would take away biodiesel, for instance, from other sectors, so it's always a competition between sectors. Airbus aircraft are able to fly on 50% SAF. I've included some links on the negative CO2 emissions values. Might be interesting for you to look into. And it's all terribly expensive currently, and expected to be so until 2050. I think another short break is in order. Thank you. I think we can take flight again, because now comes the most interesting part of the lecture: laws and regulations. Fuel blend mandates, carbon tax, efficiency mandates, I suppose, and the French flight ban. Right, so the context for this is that business has historically been and continues to be tough. This is airline net profits from the 1950s until today, with the line for COVID essentially going down up until here. So in this context, 5 different relevant regulations or laws have been enacted over the past years. We have efficiency limits enacted at the international level by ICAO. We have what is essentially a carbon tax, also ICAO, under the CORSIA scheme. We have fuel blend mandates within the European Union, a carbon tax within the European Union, and we have the French flight bans. If you should ever find yourself in the unfortunate position that you would actually need to go to the corresponding law, I've listed them here. If you're fortunate enough not to, then this will suffice. So, fuel blend mandates. The European Union, as part of their European Green Deal, has introduced a Fit for 55 package, where they want to reduce carbon emissions by 55% compared to 1990s levels. And as part of this, a law has been passed that mandates how much the blend of non-fossil fuels has to be in all aviation fuel. So it's a mandatory minimum and a successive increase. This is what the minimum looks like. So we're currently in 2025, was it like 3%? In 2050, will be in excess of 60%, and of that, 18% need to be synthetic, so non-bio. Is there currently enough fuel to fill the demand? Well, sort of, only for domestic routes if we use all the biodiesel that's available to us. According to McKinsey, that was the source for the availability of the lignocellulosic biomass pathway previously, there is. But we've also seen that it's 3 times more expensive. So this is going to be a significant issue for airlines and for the paying customer. And as I've mentioned earlier, there's going to be competition between sectors. I mean, the maritime sector needs to decarbonize. There's laws for that, both nationally and at the international level from the International Maritime Organization. The automotive sector needs to decarbonize. Heavy industry needs to decarbonize. These are all classified as hard-to-abate sectors. But there is some hope insofar as that aviation is generally the most hard-to-abate sector, because unlike in the funny little Photoshop figure I had at the very beginning, you can't actually add pantographs to aircraft and electrify them. But what you can electrify is heavy industry, such as in open-pit mining. So both in Austria and in Canada, in the large open-pit mines, copper mines, the lorries are now being electrified, and this is one less sector that would be directly competing with aviation for biofuel. Carbon taxes at the European level, that's a whole another story. This is something that's been dragged through the media many, many times over the past years because there's been so much uncertainty associated with it. And it's a little complex, but the idea is this. Again, European Green Deal, Fit for 55 package, now it's a different law, and this law says that aviation, which was previously exempt from the existing ETS, the emissions trading scheme, is now added to the ETS. So currently, the ETS says that there is a cap on total emissions in the European Union, and that cap is decreasing every year. All sectors. You're exempt if you produce, I don't know, less than 10,000 tons of carbon per year, I think. But generally, there's a cap. And sectors were able to trade with each other, and this is how some sectors made lots of money. I mean, this is the same principle that Tesla Motors uses in California to, or it's one of their main sources of revenue. It's selling the carbon emissions they did not produce as offsets or allowances to other sectors. Now, what's defined in the law is this. These are emissions allowances, not offsets. The difference is emissions allowances actually need to be bought with money from the market. So this is a tax in the true sense of the word. This is money that goes into the coffers of the European Union and is used in 2 funds that is supposed to leave no one behind, the usual, invest in infrastructure and clean energy. But it is a tax, unlike offsets, which is essentially I build a wind turbine in Nigeria, or I don't deforest a plot of land in the Amazon. Relevant emissions are currently only inter- or intra-European flights, including the European Economic Area and Switzerland. But all emissions need to be traded from 2026. Up until recently, there were very generous free allowances as part of this scheme. The only reason why you don't have to pay this carbon tax on all flights leaving the European Union, which was the original intention of policymakers, is because CORSIA, the international scheme, would be competing with it. So what does that look like? Because that's a bit dry. This is what that was supposed to look like. I started this figure in last year, and then for some reason the European Union decided to change many things, and I had to update it. So this is what it actually looks like now. We have emissions, so EU aviation emissions on the y-axis on top, with a forecast. Blue is free allowances. This is handed out to all operators under some transitional scheme. Orange is auctions. So these are allowances that Swiss needs to buy from the Swiss government, and Lufthansa needs to buy from the German government, and Austrian Airlines needs to buy from the Austrian government. The price is somewhat different than the actual spot price on the free market, but generally the same. And all the green bars, these are allowances that need to be bought on the free market. That means from other sectors, generally. How expensive is an emission in the European Union? Well, you can see that on the bottom. It's around 100. there's been different phases in this emissions trading scheme, and sectors were added to the phases during the phases. Most recently, aviation has been added. And so price has been fluctuating. And the reason for the fluctuation, there's many reasons. One is some sectors have it easier to decarbonize and they can sell emissions, but other sectors that might be growing more significantly have it difficult to decarbonize, so then that's supply constraint and so on and so on. But what you can see is that up until 2026, there's still some free allowances, and after that, for every intra-European Union and European Economic Area and Switzerland flight, you need to buy allowances for all the emissions at the price essentially here. And there's different forecasts of how that will develop, anywhere between 100 and 300 up until 2030. So that's interesting. Now, of course, the question is, how does that affect you as a consumer, or how does it affect you as an airline executive or someone working for an airline? Well, for that, we would need to know what share, or what the share of expenses is roughly. There is data for that, fortunately, for all American airlines. We can see that, well, the one thing we can see is that fuel was essentially completely free up until the oil crisis. So wouldn't it have been fun to drive a large American car in the 1950s? It got very expensive then, and we can see that the share of fuel in total expenditures of airlines has increased from like 10%, that's the purple bar, to in the order of 30% today. And on top of that, carbon tax. How have ticket prices actually developed? Well, they've only gone down, which is really impressive. This is again data for the United States, on domestic routes only, unfortunately. And this is again an apples to oranges comparison, and I apologize for that. But what you can see is that if you adjust for inflation, train travel has remained as expensive or as affordable as it was in the 1950s. Who would like to object to that? Or what am I missing? Well, one thing I might be missing is that actually consumer experience has significantly improved. There's no more third class unless you ride Deutsche Bahn, then the second class is essentially the third class. There's generally air conditioning unless you ride Deutsche Bahn, so that seems to be a recurrent theme here. But so consumer experience is not captured in this metric. And dare I say, consumer experience has had a somewhat reverse correlation in economy class air travel. But point being, ticket prices have essentially fallen since the 50s, but will now stop to do so. Unless, of course, you believe what the European Union says, which says that including aviation in the emissions trading will not directly affect or regulate air transport tickets or the ticket prices. The impact on ticket prices will probably be minor. And this is a classic example of trying to have your cake and eat it too. The Swiss version is displayed here. I mean, if the carbon tax is so low that it doesn't impact ticket prices, then how is it going to affect carbon emissions or fuel spending? So you can do a simple calculation, ballpark estimates, because we don't know the carbon price in 2030, which is the main unknown, and we don't know the fossil fuel price, and we also don't know how much SAF people will be using. But anyway, from Zurich to Athens, in an A320neo, brand new, seat load factor 100% is what I'm assuming here. Fuel sets you back around 18 euros. And on that same route, in 2026, carbon tax will be almost as expensive as the fuel. In the successive years, of course, that will be higher. And that's all fine, but it is rather humorous to make the statement that ticket prices will remain the same. Now to something more fun, which is carbon offsetting, which is the international scheme. The reason why we're not paying European Union carbon tax on flights departing the European Union. This was not part of the European Green Deal or the Fit for 55. This was part of an independent legislative package that was agreed to by the Assembly in, was it 2016? And the idea here is that up until, I'm guessing 2026, it's voluntary for member states of ICAO. After that, it's mandatory. And flights between member states are taxable in the sense that there is a CORSIA emissions unit associated with each flight. Now, a CORSIA emissions unit is different, and it's importantly different from an EU ETS allowance. A CORSIA emissions unit can be compensated by using an offset. And that could really be planting a tree somewhere or investing funds to build wind turbines somewhere in developing nations. Also, to make this a little more complex, and this is only half of it, this is not relevant to the exam, by the way, it doesn't apply to operators specifically. So if Swiss fly, well, it's a bad example because they're based in Europe, but if an airline out of Havana, Cuba, flies to Montreal in Canada, then what they actually have to pay for is not the entire emissions, but the emissions that would result from additional growth over the 2019 baseline. You can see this is getting really, really complicated. And I wasn't joking when I said this was only half of it. So you can have a look in the relevant ICAO documents. There is transitional periods where you're paying only for the offset that occurs at the sectoral level. So if the entire aviation sector grows by 20%, you have to pay for the essentially 20% more. And then at some point, the allocation changes. So then you have to pay for 15% of your own growth emissions and 80% or 85% of the sectoral growth emissions. It is really complicated. And the emissions that you do have to pay for which you're not already using biofuels or synfuels, you can compensate by offsetting. So when compared to the European measures, it's not very effective, or it's very likely not going to be effective. This also results in a patchwork sky of regulations. So what you can see here is, this is again outdated, so I'm in a bit of an unfortunate position. Some of the lecturers, especially in Aviation 1, they teach things that are time-tested and true, will never change, and I have to update my lecture slides every year. But what you can see here is, this is how the European Union envisioned this originally. A flight from Lisbon to Athens, you would pay EU ETS, so carbon tax on the entire flight. A flight from Havana to Paris, you would have to pay only for the parts in European airspace, and on the rest you don't have to pay at all, because Cuba is not a signatory to CORSIA. On a flight from Canada to Paris, you have to pay EU ETS on the European parts and CORSIA on the other. And the same goes, for instance, for a flight from Helsinki to China, to Hong Kong, where China is a signatory. This would have, of course, been a nightmare, simply the reporting duties. So they changed it to something looking more like this, where if you fly to, so the proportionality was dropped. If you fly from Helsinki to Hong Kong, you have to pay CORSIA because it's not an intra-EU flight, and China is a signatory to CORSIA. What they are trying to do is nudge countries into entering CORSIA, at the very least, by saying if, I believe, by 2027, the country to which you fly is not a member of CORSIA, you have to pay EU ETS, and that is a lot higher, of course. They will reevaluate whether CORSIA works. My guess is that this is going to be another fight with industry lobbies. But up until 2026, flights departing the European Union and arriving from abroad are not taxable according to EU ETS. And now for one of my favorite parts of the research I did into the legislation. How many of you at least heard about France banning domestic flights? Yeah, so it's been in the media, it's been in the news, it's been widely reported. How many of you think they've actually banned flights? Yeah, okay. So in 2016, the Yellow Vest movement started, and I'm not going to go into the details because I'm also not qualified to talk about this, but in response, the French president convened a citizens' assembly of, I think, 150 randomly selected citizens, that were to provide suggestions of a more equitable transition to net zero. Because the Yellow Vest movement started in response to higher taxes on fossil fuels. And then what actually happened is they provided some suggestions, and one of those suggestions was to ban domestic flights. What they said more specifically is ban domestic flights on routes where the train takes you there in less than 4 hours. So those would be most routes in France, because for all the centralized rail infrastructure, most journeys to and from Paris can be taken in under 4 hours. What happened was when this bill became law, it was significantly watered down, now only applying to trips where the train takes you there in, I think, 2.5 hours. And also additional measures were introduced, such as less than 2.5 hours, no change of trains, and 8 hours of presence at the destination, and a certain frequency of trains. Now, the smart thing where industry lobbying came in again was that actually the airports were taken as destinations and not the city centers or the train stations. So what that meant was, if you want to go from Paris to Bordeaux, what counts is not the trip time of the train between Bordeaux train station and Paris Gare du Nord, or wherever the train takes you, but between Paris Charles de Gaulle and Bordeaux airports. So there's no direct connections, the frequency is not according to the specifications, and there's no 8 hours of presence. So even though, well, I maybe should specify this, even though in theory Paris, Nantes, Bordeaux, and Lyon should have been banned domestically, you can still book tickets for the flights. Because what the French government decided before they passed the law, in order for the law to be compliant with EU rule of law inspection, was that they had originally wanted to also or explicitly include in the ban feeder flights. So if you want to fly from Bordeaux to New York, you'd fly from Bordeaux to Paris, and then from Paris to New York. This would be a feeder flight. But the EU said this would somehow constitute unlawful discrimination of intermodal competition. So they said, we'll just stick to the specifications we have, 2.5 hours, frequency, no change, etc., etc. And now you can actually still take all these flights. I think some minor routes that don't go to hubs have actually been have ceased to operate, but there's certainly not been any media reports on this. So this, I think, is more a textbook example of how lawmaking operates than it has any real bearing on increasing the efficiency or decreasing carbon emissions in France. Something similar happened in Austria, which I'm also going to include for completion. So this is a de facto flight ban. As part of a bailout package during COVID, Lufthansa Group agreed to drop 2 connections, but this was entirely voluntary. Since the money has been paid back, I don't think there's any legal reason they still have to abide by this agreement. But they have dropped it nonetheless. If we have an initial assessment, or if we were to make an initial assessment of these bans, well, I mean, they've been lip service to this. They've been lip service essentially in France, especially in the context of the Citizens' Assembly. If you look at the data, there's been one survey of 18,000 French households, people that live along the routes that were to be subject to the bans, so Paris, Nantes, Bordeaux, etc., etc., etc. 90% of them take the car anyway. A 2010's car, if 2 people are riding in the car, has around the same CO2 emissions per kilometer per passenger than a fully loaded A321neo. So it didn't do a lot of things there. No hub route ended up being banned. And the same for the Austrian case. The 2 routes were 90% feeder flights. One thing to mention here, at least, is that for feeder flights, there is ways that seem to be working really well. If we consider the economics and the statistics, this is known either as rail and plane or fly and ride. This is, of course, aptly named the engine here, the Flugzug. It's essentially being able to check in your luggage at a train station, a major train station, and replace the feeder flight with a train connection. Now, before we close, briefly on carbon offsetting. This has been decried, not just by researchers, but also by industry. So even the CEO of United called most carbon offsetting programs fraud. I think he was essentially correct in his assertion here. I'm going to skip the definition. It's essentially if you have a market that requires you to offset things, then your ability to offset things is called a carbon offset. But I'm going to mention the 4 properties of a good carbon offset: additionality, leakage, permanence, and verifiability. They're all rather self-explanatory. Additionality essentially means that the measure you take wouldn't have happened otherwise. Leakage means that, well, the carbon is either sequestered or remains bounded for some period of time. Oh, sorry, that's permanence. Leakage would be that there's no rebound effect, which in itself is a bit of a moral issue. And verifiability needs no further explanation. Of course, on the moral aspect of this, a naval blockade of an island nation would fall under all of these parameters and be an effective carbon offset. So there is clearly a moral dimension that needs to be taken into account. If you look at the carbon offsets that airlines actually have implemented, we can take a look at the Lufthansa group. They're using Compensate, which I think is a startup that was either acquired by Lufthansa or was an in-house spin-out. This is actually rather interesting. With Lufthansa, you can choose between offsetting your emissions now, which would be purchasing sustainable aviation fuel, or purchasing it X years, and I think the X is capped at 10 years into the future. In this case, that would be, is it planting a tree? Climate project portfolio. Yeah. And just before the lecture, I actually wanted to have a look, because they have to publicize the offsetting programs. I wanted to have a look what they're doing in Austria, because evidently they're doing something in Austria. And I had a good laugh here. So Lufthansa has supplied a heat pump, a residential heat pump, to a caritative project somewhere in Vienna, and they've added 2 small rows of solar panels on a mountain hut close to my hometown. And evidently this saves them 9,000 tons of carbon emissions a year, and they've also solved the problem of poverty in Austria. So you have to give it to Lufthansa, it's really impressive. EasyJet is partnering with South Pole, which has a significant presence here in Zurich. What they do is mostly social projects. Theoretically, most of these social projects don't fall under the don't qualify for leakage, but this should be a good reason for you to actually doubt whether leakage is a good metric to measure these offsets. So that essentially means, well, if we supply wind turbines to, does it actually say, to Argentina, people will use more energy, or they will become more wealthy, and then they will spend carbon on other things. The final piece of legislation is, of course, efficiency standards, essentially like the EU efficiency labels for appliances, except for aircraft. And wouldn't that be fun if you actually board the aircraft and it has the little sticker, like on your fridge? So these are just for illustrative purposes, unfortunately. The metric the United Nations, ICAO, has chosen to go on with is called the metric value. And essentially works like this. It's in units of kilograms of fuel per kilometer, and it takes into account the usable space within the aircraft. And so it's dependent on max takeoff weight, naturally. And these are going to be the standards. And because I was smart, I didn't actually include from when this is going to be effective, but you can just look that up for yourself. Anything above the line is going to be prohibited. And you can see that this is going to affect new aircraft and current aircraft in production to which changes can and should be made. This is essentially the equivalent of the Euro norm, the Euro emissions norm for aircraft. Okay. Before we close, and maybe I should have mentioned this a little earlier, there's going to be a small apéro after the lecture. No one's hungry, that's interesting. Outlook. So we've talked about the 3 levers which we have to actually decarbonize aviation: increasing efficiency, decarbonizing fuels, introducing various kinds of laws and regulations. Within laws and regulations, we've talked about mandatory fuel blending, flight bans to whatever effect they actually have, efficiency labels, etc. Now, where do we actually stand? Well, the really exciting aircraft, i.e. fully electric aircraft, aren't really getting much traction now. Yes?
Why did you cross the technology hole?
Because the project has been suspended. So this was, I think it's very recently been suspended because apparently the batteries don't have the capacity that they should have, which is as a project manager, I'm not quite sure how that would work. I suppose at the very beginning of your project, you would say, under the most optimistic assumptions, your battery will be able to power the aircraft. No. In any case, these are small aircraft that are currently in service. So we have a Pipistrel Velis Electro. These are already flying in smaller aerodromes in Switzerland. The Diamond EDA-40 is going to be in service with Lufthansa Flight Academy out of Grenchen soon. Aviation Alice has lots of orders from DHL on small freight feeder flights. And Hart Aerospace evidently is going to decarbonize all Norwegian commuter flights from 2030. I think this is first flight, not introduction into commercial service. So these aren't a lot of prototypes. For hydrogen aircraft, it looks a little more optimistic. We have various projects in which retrofits are happening. So in either the DOE 228 or in the de Havilland DHC-8. Hydrogen aircraft, of course, have a long tradition. The Soviets tried to have aircraft be powered by hydrogen because they have large natural gas reserves all the way back in 1988, but that never really got off the tracks. There is a project at ETH, a student project, if you're interested, that is actually building a hydrogen-powered aircraft, I think 4-seater. But up until Airbus intends to introduce their new Zero-E family in the 1940s, I think it's very unrealistic to have hydrogen aircraft take to the sky. Now, I've been asked about this, so I included it in the lecture, is supersonic, and not just supersonic, because who wants to travel between London and New York in, 2.5 hours? We need to do it in 40 minutes. Hypersonic aircraft, all powered by green hydrogen. There's 3 projects currently, 2 in the United States, 1 in Switzerland, actually, in Canton of Vaud. But I would caution you against giving them too much credit or expecting their products in service anytime soon. One reason for that is all you need to do is go back to that reference certainly is wrong because that paper wasn't published in 2016, but go back to the 1960s when the Concorde was actually in service, and what you can see is that, well, if you actually want to introduce supersonic or hypersonic aircraft at a large scale, what you will end up with, if you use them in the way in which they were originally intended, i.e. breaking the sound barrier anywhere and not just over uninhabited territory or the ocean, you'd end up with something like, what is that? A widespread public reaction, damage to glass and plaster in London every 1 out of 100 flights. So I think it's, unless NASA's X-59 Quest aircraft that is trying to reduce the supersonic boom into what I think they call the supersonic thump, has any chance of succeeding, this is very much unrealistic. Also, the question is there actual research interest? Do we actually feel the need for speed?
The need for speed.
Well, unfortunately, the answer is no. It's actually rather interesting. From the 1950s, the research interest in supersonic aircraft has remained roughly constant. Very much unlike what I've showed you at the very beginning, interest in sustainability. This about concludes the lecture. I think the question that you should be asking is, do you have all the answers now? I certainly feel I don't. Otherwise, we'd have me on the cover of Nature Energy very soon, having solved all the economic and sustainability issues of sustainable aviation. It's going to be a question of how stringently is the European Union and ICAO going to implement these fuel blend mandates and carbon taxes? Because otherwise we will have no incentive to switch to non-fossil fuels. I've shown you the price range. It's about 3 times what that costs you currently, with some of the pathways, the fuel stock availability being a significant issue. But the good thing is that I'll be able to update this lecture every year, and then we'll see where this goes. I have a small reading recommendation for those with an interest in the history of air transport. All these books are absolutely outstanding. I recommend them, maybe on your off time. And with that, I hope you have some questions for me. Thank you. Yes?
Yeah, I'm still not sure about flight plan. So this sort of flight you said expensive, you can still buy the ticket. It's like
Yeah, so flights to and from Air France hubs are not banned because the destination of this trip, which determines whether the flight would be replaced, is actually the airport and not the city center. And if you actually say the airport is the destination, then in many cases there's no direct connection. You don't have 8 hours on site. You don't have the frequency, etc. So it's an ineffective flight ban at best. Please.
What do these 8 hours mean? I don't understand.
So you need to be able to be on site for 8 hours. So if you drive from Paris Charles de Gaulle to Bordeaux, you need to be able to be in Bordeaux for 8 hours and then return to Paris. So there needs to be a connection early in the morning and late in the afternoon, depending on the travel time. This made it into the law. This wasn't part of the original proposal. Please.
Maybe a question on the economics of these carbon certificate markets and auctions.
Mm-hmm.
So you mentioned that, like, for the auctions, the airlines need to buy within the countries.
Yes.
Correct.
Yes.
So how does that work? What I would imagine would happen is that, like, you have like one huge player, as in Switzerland, and that basically outbids everyone at the auction, or like, and then basically the auction doesn't work anymore, right?
It doesn't work unless the price, of course, rises above the market price. Then whoever is outbid just buys from the market price. I'm not even sure how that would work in Switzerland in practice. But from what I've seen, the price for the auction for one EUA, EU allowance unit on auction, is the same as a spot price unit. And that's around 100 currently. But this is going to be a non-issue anyway, very soon. But it's a good question.
I wanted to ask about the supersonic flight, where you said the problem is the sonic booms everywhere. But surely, for certain routes, especially those across the Atlantic or large oceans, you can wait until you're over the ocean until you accelerate up to whatever.
Which is essentially what the Concorde did. Yes. So the 3 players which I've listed here, I think Hermeus and Boom actually provide to their investors, because these are private companies, they're venture capital, essentially aviation venture capital, provide to their investors reports where they estimate the demand on specific routes. And interestingly, on over-ocean routes, the demand is very low. You've got the usual suspects like Europe to the East Coast, but they estimate or they forecast a large domestic market in the United States. And you can't really do anything there. To my surprise, there was almost no market from, for instance, the West Coast to Australia, which would be another opportunity to simply break the sound barrier. But I think it's going to be up to NASA to develop something along these lines. I just thought I would include this because they're all supposed to be powered by green hydrogen, which is the only way you can get investor money nowadays. So I would be somewhat skeptical of that.
If someone, I don't know, in your opinion, decided that we have to, from tomorrow onwards, use sustainable aviation fuel, how that would translate into price of tickets?
Well, I've got one slide that sort of gives you an idea of how that would translate. Currently, around a third of the price is fuel, and then multiply that by 4 or 5. Yeah, which is this short calculation I was able to provide here also. So I mean, you can look up what flights to Athens cost currently. For this example, in 2026, I used current fuel prices. So it's not going to make flying prohibitively expensive for ETH graduates. It's going to make flying prohibitively expensive for the people that only were able to fly as a result of the significant decrease in ticket prices. I'm not quite sure how an equitable aviation transition would look like. Well, thank you very much. Yes?
Just related to that, do you know how the money is supposed to be used that is collected by this tax?
Yeah, it really depends on who you're paying the tax to. So at the international level, it's offsets. So you can essentially decide who to give your money to. A project here, there. These are private companies that need to be vetted, but that's it. In the European Union, there's two funds. One is, I think, called Structural Development Fund, and another one, I think, has the word equitable and transition somewhere in it. And then it's up to EU lawmakers to determine where that money goes. The idea really is to develop infrastructure in some of the countries that joined the European Union after 2004, research into whatever, it's tax money. So there's no legal requirement for it to be spent on things related to sustainability, I think. All right, we have prepared a small apéro for you to network with sustainability and aviation in mind. I would like to thank you very much for your attention, and I'll see you outside.